In the first fraction of a second after the universe began, matter and antimatter filled every point in space in nearly equal amounts. The physics was simple, almost perfectly symmetrical. For every particle of matter, an antiparticle. And when the two met, they annihilated, releasing pure radiation and leaving nothing behind. That was the expected outcome. That was what the math predicted. Instead, you're here. Every atom in your body, every visible star, every catalogued galaxy, all of it is the remnant of a process that should have erased itself. The entire visible universe exists because roughly one extra particle of matter survived for every billion pairs that destroyed each other. 1 in a billion. The whole structure of reality rests on that margin. Physicists have a name for this: baryon asymmetry. It isn't a fringe concern. It appears in standard cosmological models and sits at the core of the world's largest accelerator programs. The problem isn't hidden. It hasn't been solved. In 1967, Soviet physicist Andrei Sakharov outlined the minimum conditions required for matter to survive at all: violations of baryon number, violations of charge parity symmetry, and reactions occurring outside thermal equilibrium. Those aren't answers. They're a checklist, a list of what would need to be true. The mechanism that produced the right surplus remains open. In 2025, researchers at CERN's LHCb detector confirmed matter-antimatter asymmetry in baryons, the particles that include protons and neutrons, the building blocks of everything visible. It was a real measurement. It confirmed the asymmetry operates in specific decay processes. It did not explain why the early universe ended up with enough matter to become a cosmos. The laboratory sees the symptom. Cosmology is still searching for the mechanism. Underneath that search sits a second, quieter problem. If the surplus of matter was already improbable, the existence of a universe capable of producing it may be more improbable still. Some inflationary models treat the origin as a quantum transition, a shift from an unstable state into something that could expand and cool. In physics, nothing doesn't mean an empty room. It can mean a vacuum configuration where the usual concepts of space and time don't yet apply. Why any such configuration existed, why there were rules at all for the asymmetry to operate within, remains unanswered. One extra particle per billion became every atom that ever formed. The data doesn't call that a miracle. It calls it an open question, which, depending on how carefully you read the numbers, may be the more unsettling framing. Even before the last particle found its place, the ground beneath reality was already uncertain. Matter had survived, but the state it inherited, the vacuum, the field configuration that physics calls the lowest energy state, may not be as stable as it looks. In modern quantum field theory, the vacuum isn't emptiness. It's a condition, a specific arrangement of all the fundamental fields that govern how particles behave, how forces operate, how the rules of physics hold together. And for the last several decades, calculations based on the measured mass of the Higgs boson and the top quark have placed our vacuum in a category that carries a precise and uncomfortable label: metastable. That word doesn't mean dangerous in any immediate sense. It means something subtler. The current vacuum could be not the lowest possible energy state, but a local minimum, stable enough to persist but not the deepest configuration available. If a region of space somewhere spontaneously transitioned to a lower state, it would expand outward as a boundary between two different sets of physical laws, not an explosion, a rewrite. The rules governing chemistry, atomic structure, and the forces holding matter together would no longer apply on the other side of that boundary. And because the boundary would travel at nearly the speed of light, no information about it could arrive before it did. The official response here is measured. The expected lifetime of the metastable vacuum exceeds the current age of the universe by many orders of magnitude. Statistically, this is not an imminent concern, but the category shift matters. The vacuum is not described as unconditionally stable. It is described as probably long-lived. Those are not the same thing. While that calculation was being refined in particle physics, a separate set of measurements was arriving from a different direction entirely. In the late 1990s, teams studying distant Type 1a supernovae expected to find that the expansion of the universe was slowing down. Gravity should have been pulling everything back, gradually decelerating the outward motion left over from the early universe. Instead, the data showed acceleration. The expansion was speeding up. Something was pushing space apart with increasing force, and it wasn't any known form of matter or energy. That something was named dark energy. It now accounts for roughly 68% of the total energy content of the universe, according to measurements tied to the Planck mission. Its physical nature remains unknown. It doesn't emit light. It doesn't interact with matter in any detectable way beyond its effect on the expansion rate. The models that describe it work mathematically. They do not explain what it actually is. What dark energy means for the long-term fate of everything depends entirely on its behavior over time. If it remains constant, the universe expands forever and cools. If it grows stronger, it eventually overcomes not just gravity between galaxies, but the forces binding galaxies themselves, then solar systems, then planets, then molecules, then atoms. A sequence called the Big Rip. Most current measurements place its behavior close to the boundary between those two outcomes. Not conclusively on either side. The vacuum may be temporary. The force driving the expansion is unnamed. Two of the most fundamental properties of the space matter inhabits are either uncertain or unknown. The structure survived the birth. What it's standing on is a different question. The most likely end of the universe will not look like a catastrophe. There will be no shockwave, no signal, no moment when instruments record a threshold being crossed. The process has already begun. It began the moment the first stars ignited, and it moves not through violence but through arithmetic. Energy is finite. The gradients that make processes possible are being spent, and once spent, they don't return. This is the scenario physicists call the heat death, or the big freeze. Not a freeze in temperature alone, but a freeze in difference. Every physical process, combustion, gravity doing work, a signal moving through a nerve, a star fusing hydrogen, requires a gap, a difference in temperature, pressure, chemical potential, gravitational potential. Without a gap, there is no direction for energy to flow. Without flow, there is no event. The universe doesn't need to destroy its matter to become effectively dead. It only needs to erase the differences that make matter do anything. Stars exhaust their fuel. The cold gas that would form new ones disperses. Galaxies drift beyond each other's horizon, separated by expansion into permanent isolation. Black holes outlast everything visible, then slowly lose mass over unimaginable timescales through a quantum process called Hawking radiation. Until even they are gone, what remains is a cold, diffuse, uniform distribution of particles, technically present, functionally silent. That scenario is disturbing on its own, but it carries a second problem that receives far less attention than it deserves. The projected fate of the universe depends on its composition. What dark energy does in the long run determines whether the end is slow cold or progressive rip. What dark matter does, how it clusters, how it decays, whether it decays at all, shapes the large-scale structure the whole story plays out within. These are not peripheral details. They are the dominant variables, and we can't see either of them. Normal matter, atoms, molecules, dust, gas, stars, planets, everything that has ever been directly observed or measured, accounts for roughly 5% of the total energy content of the universe. The remaining 95% divides between dark matter at approximately 27% and dark energy at approximately 68%. These figures come from analysis of the cosmic microwave background, the oldest light detectable processed through the most precise instruments ever built for this purpose. The instruments are real. The measurements are repeatable. The components they point to have no confirmed physical identity. Dark matter is inferred from gravitational behavior, the way galaxies rotate, the way light bends around clusters, the way large-scale structure formed. The inference is consistent and cross-confirmed across multiple independent methods. But no direct detection has produced a confirmed particle. Its presence is known through what it does, not through what it is. Dark energy is inferred from the acceleration of expansion, It fills the role of whatever is causing space to push outward faster over time. The models absorb it cleanly. The mechanism behind it remains unidentified. The official cosmological model works. It predicts and it matches. But a model that works mathematically while containing two unknown dominant components is not a closed account. It is a precise description of effects produced by causes that have not yet been named. The universe is mostly dark. The part that isn't is reading the instruments. There is a place where the two best theories in physics meet and contradict each other completely. Not in philosophy, not in interpretation, in the math itself applied to a single object. A black hole is not simply a dense mass. It is a region where space-time curves past a threshold called the event horizon, a boundary beyond which nothing, including light, can return to the outside. General relativity describes this cleanly. The geometry works. The predictions match every observation made so far. On paper, the event horizon is not a wall or a surface. An observer falling through it would notice nothing unusual at the moment of crossing. The catastrophe only arrives later at the singularity, the point where the equations stop producing finite values and the familiar description of space and time breaks down entirely. Quantum mechanics adds a second layer. One of its foundational requirements is that information cannot be destroyed. The total quantum state of a system must evolve in a way that preserves the information encoded in it. This isn't a preference. It is built into the mathematical structure of the theory at the deepest level. These two requirements collide at the black hole. In 1974, Stephen Hawking calculated that black holes are not completely dark. Quantum effects near the event horizon cause them to emit thermal radiation slowly, what is now called Hawking radiation. A black hole that radiates loses mass. Given enough time, it evaporates entirely. And if it evaporates entirely, the question becomes unavoidable. What happened to the information about everything that ever fell in? If the information is gone, quantum mechanics is broken. If the information survives, something in the standard picture of the event horizon or the interior must be wrong. Both options carry a cost. Neither has been paid in full. This is the black hole information paradox. It is not a philosophical puzzle. It is an active area of research that has occupied some of the most precise theoretical physicists alive for decades, producing entire frameworks: holographic duality, the island formula, entanglement entropy, each of which addresses part of the problem while leaving adjacent questions open. One detail from that research shifted the frame of the problem in a way that has not been fully absorbed by popular accounts. The entropy of a black hole, a measure of the information it contains, scales with the area of its event horizon, not with its volume. In ordinary systems, information capacity scales with volume. A bigger container holds more. But for black holes, the boundary carries the account, not the interior. This is the starting point of the holographic principle, not a metaphor about simulations, a precise physical observation. The maximum information content of a region of space may be encoded on its surrounding surface, not within the volume itself. If that principle is correct beyond the specific case of black holes, if it reflects something general about how space and information relate, then three-dimensional volume is not the primary container of physical reality. It may be a derived structure, a projection from something lower dimensional that we do not yet have a direct description of. The black hole begins as an object in space. It ends as a question about whether space, in the way we use the word, is fundamental at all. If space may not be fundamental, the next question arrives with quiet force. What about time? Of all the things physics has dismantled, time is the one that feels most resistant to revision. Matter can be energy. Space can curve. Particles can exist in superposition. But time seems non-negotiable. It is the axis every experience runs along. Memory points backward. Anticipation points forward. Cause precedes effect. The whole architecture of reasoning depends on this sequence being real and fixed. Physics has already made it less fixed than it appears. The first cut came from special relativity. Two observers moving at different velocities will measure the same event as lasting different amounts of time. Neither is wrong. Time itself dilates with speed. The second cut came from general relativity. Clocks run slower in stronger gravitational fields. This is not theoretical. It is an engineering constraint. Satellite navigation systems require relativistic corrections to stay accurate. Without them, positioning errors accumulate fast enough to make the technology useless. Time's rate is a function of where you are and how fast you move. That is not a philosophical position. It is a calibration requirement built into working hardware. But those two results still leave time intact as a parameter. Slower in some places, faster in others, but present everywhere, flowing in one direction, providing the scaffolding within which physics operates. The harder problem emerges at the boundary between quantum mechanics and gravity. In standard quantum mechanics, time enters the equations as an external parameter. The system evolves with respect to time. Time itself is not part of the system. It is the background against which the system is described. In general relativity, time is not a background. It is part of the dynamical structure of space-time. It bends, it stretches, it participates in the geometry being described. When physicists attempt to combine these two frameworks into a theory of quantum gravity, this difference becomes a structural obstacle. If space-time itself must be quantized, must be treated as a quantum system with its own uncertainty and fluctuation, then time can no longer serve as the external parameter that quantum mechanics requires. It becomes part of what needs to be explained, not the framework within which the explanation runs. Some approaches to quantum gravity suggest that time may be emergent, not fundamental, not a background, a property that arises from deeper quantum relationships, from the way entanglement between subsystems generates correlations that, at large scales, behave like temporal sequence. In this picture, time is something a sufficiently complex quantum system produces, not something the universe runs on. This is not established physics. It is an active and unresolved area of theoretical work, but the reason it is taken seriously is not speculation. It is the direct consequence of taking both existing theories seriously at the same time. General relativity and quantum mechanics each work with extraordinary precision in their respective domains. They use time differently. In the places where both must apply simultaneously, near the beginning of the universe at the center of a black hole, neither gives a clean answer, and the ordinary notion of time is the first thing to become ambiguous. The clock on the wall runs forward. The physics underneath it doesn't guarantee that forward is fundamental. Every anomaly covered so far has had a specific shape, matter that shouldn't have survived, a vacuum that may not be permanent, an expansion driven by something unnamed, a universe cooling toward a state where nothing happens. 95% of the energy content unidentified. Two foundational theories that break against each other at the same boundary. Time that may be a derived property rather than a fixed axis. Each of those problems exists within the laws of physics as they stand. They are cracks in the application of the framework, not in the framework itself. The final problem is different. It points at the framework. The constants that govern physics, the speed of light, the strength of gravity, the mass of the electron, the value of the cosmological constant, the ratio of electromagnetic force to gravitational force, are not derived from any deeper theory. They are measured. They are input values. The equations of physics take them as given and produce predictions that match observation with extraordinary precision. But the equations do not explain why those values are what they are and not something else. This would be a minor philosophical concern if the values were arbitrary. They are not. Change the cosmological constant by a small factor and the universe expands too fast for gravity to assemble matter into any structure. Change the ratio of electromagnetic to gravitational force, and stars either burn out in millions of years instead of billions, or never ignite at all. Adjust the mass of the up quark or the down quark past certain thresholds and stable atoms cannot form. Alter the strength of the strong nuclear force slightly and hydrogen becomes the only element, or no element survives at all. The window of values compatible with any complex structure, let alone chemistry, let alone life, let alone an observer capable of measuring the constants, is narrow in multiple independent directions simultaneously. The standard response to this is the anthropic principle. We observe these values because only these values permit observers to exist. In universes with different constants, there is no one to notice the difference. This is logically consistent. It is also by itself not an explanation. It describes the selection condition. It says nothing about what generates the range of possibilities being selected from, or why any particular value was realized. Some versions of inflationary cosmology propose that the constants are not universal, that different regions of a larger structure, sometimes called the multiverse, contain different values and we inhabit one of the compatible configurations by necessity. This framework makes the fine-tuning less surprising, but it does so by placing the explanation outside any region we can observe or test. It resolves the problem by extending the universe past the point where physics can currently reach. Others argue that a deeper theory not yet formulated will show that the constants are not free parameters at all, that their values follow necessarily from some underlying structure, the way the properties of a chemical element follow from atomic physics. That theory does not exist. Its absence is not a gap in the literature, it is the open edge of the entire project. What remains is this: the universe as observed is compatible with structured complexity only within a narrow range of its own governing parameters. Whether that range was selected, necessary, or simply the one instance that happened, physics does not yet say. The equations work, the values sit where they need to sit, the data closes no doors. The question of why the numbers are what they are remains exactly where it was when the first measurement was made, unanswered, precise, and unignorable.